Colloquium. It's been going on for 3 months now. And I hope this, we have as many people attending and we have an entire breadth of topics for you. Today, I'm very, very happy to welcome Tom Theuns for today's Colloquium. It's been going on for 3 months now. And I hope this, Tom will be talking about cosmological simulations and galaxy formation. And he's been he did his PhD in Belgium, and I remember first meeting him in Cambridge, where he was an advanced fellow in the mid-90s. Before that, he was a Marie Curie fellow at Oxford. But he's been at the Institute for Computational Cosmology at Durham from the mid 2000s, 2006, 2007, something like that. And he's a professor of cosmology, and of course is known for his work on cosmological simulations, which we'll hear today. I'm very happy to hand you over to Tom, but before that, I should mention that he made a particular point in saying that he would welcome questions during the talk. I mean, that's not our normal practice. We wait till the end of the talk. But if the audience today, we're willing to try this. So I would still urge people here to use the hand up icon in the participants window, and which actually makes things a little orderly. And if that doesn't attract Tom's attention during his talk, I will point out to him. Also, he says that after the talk finishes, we are aiming to finish around the hour and have some questions, but he's willing to be around for a discussion with a smaller group if people want to continue a discussion. Okay, thank you very much. So handing over to Tom.
All right, thank you very much. So I'd like to start to thank the organizers for letting me talk about my work. I'm very excited about this. And thank you to the audience for switching on. As you heard, I'm very happy to be interrupted. If you have any urgent questions, I'll stay on later on. If you want to talk to me about your own work, that would be great as well. So I'm going to talk about the IKEA model of self-regulated galaxy formation. So I'm very excited about this work. This is work I've been doing with Mahavir Sharma on the top right here when he was a postdoc in Durham. It's also very much based on my experiences and working together with the people with whom I did the Eagle simulations that you may have heard of. And the Eagle simulations, those are cosmological simulations of galaxy formation. They will also feature in this talk. If you're wondering about what is the background here, this is Durham Cathedral. I'm not actually there, but I'm at home, I guess, like most of you. So I'm going to start with introduction and motivation for why I'm coming up with this model here. And then from then, I'll go into the model. I'll compare that to both simulations and data. And hopefully there's some time later, I can talk about some extensions of the model that I've been working on. So let's get started. So this is my first slide here called Progress in Astronomy. And so as a theorist, I must confess that there's been a lot of progress in astronomy, but that is mostly observational. And these observations themselves are driven to advances in instrumentation. And I hope you all realize and see some of these fantastic pictures. It's really astonishing, I think, the progress that we've seen over the past couple of decades. And so the two things that I want to draw your attention to, I'm sure you know this, is that these advances in instrumentation have shown us galaxies in ever more detail than we've ever seen before, right? So look at this fantastic galaxy in M83, panchromatic view. You can see the spiral arms, you can see the dust lanes, you can see the star-forming regions. It's a really fantastic, fantastic image of a galaxy. And of course, we have many of those equally fantastic, detailed pictures of how present-day galaxies look like. But the progress has also been in statistics. So the bottom right panel shows you the SDSS, the Sloan Digital Sky Survey, distribution of galaxies in the universe. And so that goes out to redshift point 14, you see there. So every dot is a galaxy. The galaxy is colored according to the color of the stars in the galaxy. Red would be, non-star forming elliptical galaxies, and green and blue would be star forming galaxies. You see the distribution of galaxies, the voids, the filaments, the clusters of galaxies, right, that you see with the fingers of God pointing towards the observer here. It's really astonishing progress in astronomy over the past 20, 30 years, say. And so, as I said, this is all observational progress. So then you may ask, so what is the role of the theorist here? So I put a theoretical physicist in Google, and out in Google Images came this picture of a Stanford theoretical physicist. So what is the role now of a theorist? And so here's my view of the universe of galaxies. And so I was thinking, so suppose that before a seminar at some conference, say, you're having coffee with some famous scientist that you admire a lot. Maybe it's Newton that you're talking to, or maybe Feynman, or who is your famous astronomer or famous theorist. And you have like 5 minutes, and the famous person tells you, so what are you doing? So I study galaxies. I know very little about galaxies, this famous person says. So what is it you try to understand? And so now you have 2 minutes, 3 minutes to explain what it is that as a theorist you want to understand. And so I'm going to show you the 2 slides that I think, well, for me, is what I would show this famous theoretician. And so maybe I stop for 2 seconds to let you think if you could summarize what you as a theorist want to understand from the universe of galaxies. Which 2 slides would you pick? Okay. So while you think about this, let you show me my first slide here. Okay. My first slide here is the galaxy stellar mass function. So the horizontal axis is the mass of a galaxy. The galaxy stellar mass function at redshift 0. So horizontal axis is the stellar mass, log stellar mass from 1 million solar masses to 10 to the 12 solar masses. And on the y-axis is the number density of galaxies with that mass. So it's a histogram of how many galaxies you have per unit volume with a given mass. Then the different colors, blue and green, are different surveys. And then the black line is a fit. And so basically it shows you that there's many more small galaxies than large galaxies, right? And that this galaxy stellar mass function has a characteristic shape. We know that, of course, for a long time. Schechter already fitted this shape as a combination of a power law. So you have many more low mass galaxies than massive galaxies, and it's almost a power law in this log-log plot. And then there's some characteristic mass at the position of my pointer, and above that characteristic mass, the number of galaxies decreases very rapidly. And so you can also already see that because we have much better statistics now, it's really not a Schechter function. You can see that there's an inflection point, right? The data are good enough to see deviations from that simple picture. And surely if we claim that we understand galaxies, that's one of the things that should come out, right? What is the origin of the galaxy stellar mass function? So that was my first slide of that I was going to say that's really the major thing that we want to understand. And the second one is equally basic. Galaxies form stars, right? And that is illustrated in this plot here. So what is shown here on the horizontal axis, again, log stellar mass is solar masses, 10 to the 8, 10 to the 12 here. And on the vertical axis is plotted SSFR. It's the specific star formation rate. So it's the ratio of the star formation rate of a galaxy over its stellar mass. And every dot, again, is a galaxy. And what I take away from this plot is that the specific star formation rate is basically a constant. It's almost independent of mass. So there's some scatter, and maybe there's a bit of a trend, but more or less, the specific star formation rate is a constant at about 0.1 per giga-year. And so I would say, amongst all the plots that I've seen in astronomy, clearly, if we are going to claim we understand how galaxies evolve, you should come up with a reason of why they do like that. So those are my 2 plots. I don't know what you would have shown. So pick from this distribution which facial expression represents your reaction best. Are you howling with laughter at these simple plots that I took? Are you very angry that your basic plot is not in there? And so think about this more. Does that mean I don't care about the Hubble sequence? Yes, of course I do. What about the Madao-Lilly plots, right? The star formation history. What about galaxy clustering? What about like black holes, central galaxies, Tully-Fish relation, mass metallicity relation? You think there's an enormous number of plots that or relations that we also want to understand. But I think the two that I picked are probably more fundamental than any of these. So I'm going to skip this here. So, of course, we know a little bit about the origin of these relations. So, for example, this is looks very curious the way I've plotted it. It's because it's an observational plot where you have luminosity on the horizontal axis and you have color on the vertical axis. And so you see a distribution of blue points. Those are star-forming galaxies. They are physically blue. And red points, these are non-star-forming galaxies, elliptical galaxies, say, right? So there's more to it than that the galaxies are forming stars. So the inset shows you a movie of how galaxy color evolves as a function of stellar mass in the Eagle simulations. And so I'm going to go back. So at high redshift, galaxies are much more star forming than at low redshift. See what I can stop that. And so here you have the sequence of star forming galaxies in Eagle. And here you have the sequence of non-star forming elliptical galaxies. And so there's more to it than what I was claiming in the beginning, that there's a star forming sequence. There clearly is a star forming sequence. At lower redshifts, you also have a cloud of non-star forming galaxies called the red sequence. But the other thing that you should see in this plot here is that the specific star formation rate increases very rapidly with redshift. At higher redshift, the specific star formation is much higher than at lower redshift. So that's another thing probably we want to understand. So here is in the Eagle simulation, the Hubble sequence. So you have these galaxies and you have elliptical galaxies. Another thing we may want to understand, but maybe slightly less important, I would argue, than understanding these basic plots. So here again, I want to at least understand and uncover the basic underlying physical process that gives rise to these plots. And in fact, let me be even a little bit more approximate. So if we look at this galaxy stellar mass function, I was talking about the Schechter function, and then I was already saying, well, it's slightly different from a Schechter function. So I spotted, as did Schechter in 1970s, that the low mass end is a power law. Okay, so if it's a power law, what is then the slope and what is the amplitude? Clearly, if we're going to claim we understand galaxy evolution, that is something basic we should be able to understand. And then what sets this characteristic mass above which the number density of galaxies drops significantly? So that at least, a theorist should be able to explain why that is. Where does the slope come from? What sets the amplitude? And as similarly for the specific star formation rate plot here, stellar mass, specific star formation rate, amplitude here, what sets this amplitude? Okay, why is the slope 0? And why is there such a strong redshift dependence? Okay, so if that's what I set out as a theorist to describe and understand, where to start from. So suppose that you knew nothing about this yet, and you're talking to somebody during coffee or tea in some astronomy institute, and they say, why don't you go to talk to Bob, say, a specialist in galaxy evolution? He knows a lot about star formation. Why don't you go and talk to Bob? Okay, and so Bob is not some real person, so don't be upset. So Bob comes up with this plot here and says, I know, I've been studying star formation for a long time, so I know stars form in molecular clouds. Okay, then massive stars have supernova explosions. These stars also produce dust. You have to make pulsars. You have X-ray binaries. These supernova, they eject stuff that enters this interstellar medium that makes clouds and makes stars, and that's what you need to understand. Okay, and so in the background, I wrote headache starting, right? Because that is very, very complex physics. It's non-linear. It's not clear where to start in this. For example, why does it explain that the star formation rate, the specific star formation rate, is the same in all galaxies? What is it that changes in this picture? If you go to higher redshifts, why does the star formation rate increase with higher redshifts? It's unclear from this picture here. So I would say if you start from this, that is going to be very, very hard, because this will be very, very difficult to understand. So I want something much simpler. Okay. So I'm now depressed because I don't know how to get started. So I go back to the coffee room and I run into somebody that does numerical simulations. And they say, well, we've solved this all because numerical simulations, they describe all what you've been wanted to explain. So for example, here is the galaxy stellar mass function. The different panels are at different redshifts. Then the symbols here are the data. So this is the function that I showed you before at redshift 1. Here is at redshift 1, at 2, at 3, at 4 rather. And then the different models are either semi-analytic models, so models of galaxy formation, or numerical simulations. And they really capture some of that. Of course, some of them capture these better than others, right? So for example, you see at redshift 4, maybe some of them don't describe the data in great detail, but at redshift 0.1, it's relatively okay, right? So then you say, oh, that's very promising. So then that means that you understand what is the physics that sets this. Okay, so then you start reading some of these simulation papers, and it's a disaster because they all do something different. Some simulation papers will say, so this is the way we do star formation. We have a star formation threshold. Then the star formation rate depends on this. And very crucial is the magnetic fields, say, in the simulation. And then you read another simulation paper, and they don't have any magnetic fields. Yet they reproduce the data just as well. And so now I'm depressed again, because not only do these simulations do quite complex modeling, it's also different, and they all say different things. So now I don't know what to believe anymore. So that's maybe not very promising either. So here is a starting point. What I want in my theoretical modeling, I don't necessarily care about reproducing everything in detail. I want some simple, easy to understand mechanism that explains why all these galaxies do this thing. Because think of these different simulations, they all do something different, yet they get to the same answer. How is that possible? How can you make galaxies in completely different ways, yet they have very, very similar properties? And so the basic physical driver that I'm thinking of is self-regulation. Well, I've thought of that before. Boucher in 2010, 10 years ago, and there's a whole series of papers that argue exactly that it's self-regulation that make the population of galaxies as we observe it. The thing is, self-regulation means something different to different authors. So for example, maybe the self-regulation model that you've heard of is the gas regulator model or the bathtub model by Lilly 2013. So what they say is that what regulates star formation in a galaxy is the gas reservoir. So their argument is, if a galaxy has a lot of gas mass, then it will make a lot of stars. Those stars decrease the gas mass, and that decreases the star formation rate. Okay, and that is a self-regulation thing. So that may be true or not. It does leave me with some questions. For example, what sets the gas mass in a galaxy then? Okay, so have I not moved the problem of what sets the star formation rate to what sets the gas mass? And more worryingly, I think, it means that this whole physics of what sets the star formation rate now depends on the star formation law. That is, what is the relation between the amount of gas you have in a galaxy and its star formation rate? And so now we're back to, what is the rate at which you form giant molecular clouds? What fraction of giant molecular clouds form stars? This whole complex thing of star formation is then what sets what is the star formation or the rate of a galaxy. And that I find very complicated. So let's think of something completely different and another astronomical system that is very strongly self-regulating, and that is a main sequence star. So this seems like a very big departure of galaxies, but hang on with me for a second. So here's the Hertzsprung-Russell diagram, right? Temperature of a star versus velocity. Here's the main sequence. Here's the sun. And what I've always found surprising is that main sequence stars live for such a long time. For example, for the sun, the dynamical time is 20 minutes, right? That's the time for a sound wave to cross the sun. Yes, its lifetime is 10 billion years. How can it be that a physical system is able to survive for so many dynamical times? That sounds like something must regulate main sequence stars. This is, of course, very well known. I'll just take you through this. So the answer is self-regulation, right? A main sequence star lives so long because it's self-regulating. I'll explain you what is necessary for that. So if I were to say that the rate at which a main sequence star produces energy through to nuclear fusion, this E dot nuclear, that it's equal to its luminosity, then you would say, yes, obviously, right? Obviously. The question is, why is that equality? Why is that an equilibrium situation? Okay, and there's two properties of a star that you need to have for this to be truly self-regulating. The first is that stars have a negative specific heat. That basically means that if you extract energy from a star, rather than cooling down like every normal thing would do, it heats up. That's negative specific heat. And the second thing that you need to have is that the nuclear energy generation rate increases with temperature. And it, in fact, it increases very rapidly with temperature. It goes like the temperature to the 4 for the PP cycle, like temperature to the 16th for the CNO cycle, and like temperature to the 40th or something for the triple alpha process. So what is the connection between this and self-regulation then? So I need to take a step back and remind you that the star, of course, is in hydrostatic equilibrium, and a consequence of that is that it's in virial equilibrium. So that means that the energy of the star, E here, is the sum of its gravitational energy and of its thermal energy, and that is equal to half the potential energy or minus the thermal energy. That's virial equilibrium. And so that means the derivative of the energy over the temperature is negative. That's negative specific heat, right? And so why is that so crucial for self-regulation? So suppose the star is not in equilibrium. So suppose the rate at which it produces energy through nuclear fusion is less than its luminosity, say, okay? So the star is now losing energy faster than it generates it. That means that the energy becomes more negative, right? Or in absolute value, the energy increases, right? But because the energy is minus the thermal energy, is the absolute value of the energy increases. That means that the thermal energy increases, so the star heats up. That's this negative specific heat. And because the gas gets hotter, nuclear fusion increases, the nuclear fusion rate increases, okay? And so that is stability, right? If the nuclear energy generation rate is too low, then processes will happen in the star to increase it, okay? And so the conclusion, nuclear fusion in main sequence stars is secularly stable, provided the nuclear energy generated increases with temperature, but the rate or the power doesn't actually matter, right? The details of nuclear energy generation do not matter to explain the longevity of main sequence stars. Okay, so that's a beautiful example of stability, and that's of course very well known. It's right in all the textbooks. So this I thought was a very neat way of making something stable. So can we apply similar reasoning to galaxies? And the answer is, well, no, I don't see how you can apply this. For example, I don't understand what is the process that I should associate with the luminosity. Should that be the luminosity of the galaxy or something else? And also, I don't understand what the galaxy analog of nuclear fusion is. What are you thinking of? But it's a very neat stability. But I don't know how to apply this. So let's try to think a bit more how you can apply this to galaxies. First of all, surely, right? Surely, in boldface, the dark matter that binds the galaxy, that needs to play some role. Okay, so let me think a bit of things I know about dark matter halos, and there's 3 things that will play a role in the IKEA model. First of all, dark matter halos evolve in virial equilibrium. I'll show you. I'll demonstrate that. They do so at constant concentration. I'll show you that. both these things are pretty well known. And then third, maybe slightly less known, their energy changes due to cosmological accretion. Okay, so let me show you 1, 2, and 3 more detail here. So what I've plotted here as a function of redshift is the virial ratio of a dark matter halo. So these are not galaxies, but dark matter halos. So the virial ratio is the ratio between the kinetic energy of the dark matter particles in the center of mass rest frame over the gravitational potential of the galaxy, of the halo rather. The different colors here refer to different halo masses at redshift 0, 10 to the 11 to 10 to the 13 here. And so these are results from a numerical simulation. And if the galaxy is if the halo is in virial equilibrium, then these ratios remain constant, okay? And they remain at least approximately constant, okay? Approximately the ratio between those two is a constant, independent of the mass of the halo. This is a well-known thing, okay? So you can see that's not quite constant. Below redshift 1 or so, it seems to decrease a bit. That is actually due to the onset of the cosmological constant in cosmological simulations. So these are Eagle simulations, but any other simulation shows this, and we've known this for a long time. So dark matter halos evolve in virial equilibrium. Secondly, they evolve at almost constant concentration. Maybe that's not that well known. What do I mean by concentration? So here's the gravitational energy of the dark matter halo. That is of the order of gm squared over r, right? Gravitational energy, with a proportionality constant that depends on the dark matter distribution. And so that's what I call the concentration parameter alpha here. And so here is alpha is plotted as a function of redshift. Again, simulation results for different halo masses. And approximately, along as the halo evolves, approximately alpha is a constant. Not identically, okay, but approximately. So I think that that's also quite well known. And then a consequence of those two is that the energy of a dark matter halo evolves due to cosmological accretion. It has to be true if they remain in virial equilibrium, but I haven't seen anybody discuss that, okay? So here is what I mean by the energy of a halo. So sum of its kinetic energy and its gravitational energy, and because it's in virial equilibrium, so it's minus the kinetic energy of all the particles. And so now I'm going to take the time derivative of this, E dot halo. I'm going to write this in terms of M dot halo times some parameter kappa. And what is plotted here is kappa as a function of redshift, okay? And so you see that kappa as a function of redshift is a constant, almost, okay? So that means that due to cosmological accretion, as the mass of the halo grows, its energy also grows. It becomes more and more negative, okay? But the rate is a constant. So here are the 3 things that I've shown so far. Halos evolve in virial equilibrium at constant concentration, and they change energy due to cosmological accretion, okay? So there's 3 things, relatively well-known properties of dark matter halos. And 4, halos grow in mass, and successive simulations of structure formation have determined very well how they grow in mass. So this is a fitting formula taken from Korea in 2 papers here, which gives the mass of a halo as a function of redshift in terms of the mass of the halo at redshift 0, mh0, times a function of redshift, 1 plus z to the a, e to the minus bz, where a and b are fitting parameters, are approximately those values, okay? So these 4 things of dark matter halos is what I'm going to use. They evolve in virial equilibrium at constant concentration, kappa is a constant, and they grow in mass, and this is the fitting formula for that, okay? So back to galaxies. So model for the first attempt for the evolution of galaxies, E dot halo decreases, or halos lose energy due to cosmological accretion. Remember in my analog with main sequence stars, I was going to look for some analog of the object losing energy. For a star, that was because it radiates. For a halo, it's because it grows in mass due to cosmological accretion, okay? So I found my luminosity term here for the halo. And so I'm going to say for the galaxy, well, it's something similar. It looks very similar, the red equation for the halo and the blue equation for the galaxy. The only difference is omega b, the baryon fraction, the ratio of barons over dark matter. So as the halo grows in mass and its potential gets deeper, the galaxy also loses energy because it's more and more bound because it lives in a halo whose potential, well, is deepening and deepening. Okay, so I'll use this as the analog for the luminosity of the main sequence star. So now I need the analog of fusion to come up with an equilibrium. Okay, so this is the halo. So from the galaxy, I'm going to replace the equation that I had before and add a term here. What is this term? It's the energy injected by massive stars. So as the galaxy makes stars, remember that's one of the things I want to understand. Some of these massive stars explode as supernovae, and they inject energy into the forming galaxy. And so because the rate at which you form massive stars is proportional to the star formation rate, I'm going to write this energy injection rate as the star formation rate times something which then has the dimensions of energy per unit mass. That's a velocity squared. Okay, that's v star squared. And so what is this v star squared? In fact, I can write down an equation for that. So look at this equation here. So it's my v star squared. I've written that in terms of how much energy a supernova ejects, 10 to the 51 ergs, right? Divided by how many stars I need to form before I make a supernova, about 100 solar masses of stars. With other words, for every 100 solar masses of stars that I form, supernova associated with that inject 10 to the 51 ergs in that. Okay, and then I've added two fiddle parameters, eta, which is really something that depends on the initial mass function, really how many supernova do you get per 100 solar mass of stars, okay? Something of the order of 1. And then crucially for the model here, epsilon, okay? Because most of the energy injected by supernova in the interstellar medium is lost through radiation, okay? So epsilon characterizes radiative losses. If epsilon is 1, it means there's no losses. All the energy injected into the interstellar medium remains in the interstellar medium. And if epsilon is much smaller than 1, then energy losses are very important, okay? And so here is my galaxy analog now to the star analog. So the star loses energy to radiation, but gains energy through nuclear fusion. The galaxy loses energy due to cosmological accretion, the potential well of the halo becoming deeper, but it gains energy because it makes stars as stars inject energy. So that's that's basically the model. So now the crucial question is, of course, this is all very well, it's all very theoretical, but why would this be stable? Okay, is there some reason that this is a stable equilibrium? And so the reason it's a stable equilibrium goes as follows. So again, I'm going to assume that instantaneously the galaxy is not in equilibrium. For example, this left-hand side is smaller than the right-hand side. For example, the galaxy is not making stars at a high enough rate, okay? So as the halo grows through cosmological accretion and the potential well deepens, the galaxy gets crushed more and more by the gradient of the potential, okay? As a consequence, to remain in hydrostatic equilibrium, the interstellar medium, the pressure in this interstellar medium must increase. That is viral equilibrium, right? And so what you need for this to be an equilibrium situation is that if this interstellar medium pressure increases, the star formation rate needs to increase, okay? So stability is guaranteed provided the star formation rate in the galaxy increases with the pressure in the interstellar medium. If that is true, then this relation is an equilibrium relation, okay? And so that is the essence, and that is the physical process that I was looking for that self-regulates galaxies, okay? And so this IKEA model has 4 parameters. That's why it's called IKEA. So I stands for the initial mass function. How many supernovae do you get per star formed? Kappa is this property of dark matter halos that we saw. Alpha is the concentration of these halos that we saw as well. And epsilon is the crucial parameter, which is a measure of radiative losses of supernovae, okay? So in the IKEA model, I'm going to present you, I'm going to keep the initial mass function a constant. I'll just use a Chabrier IMF. I'll keep kappa constant. I showed you that it's approximately 5/3 in simulations. I'm going to keep alpha a constant. It's about 1. That's also what the simulation shows. And so really, this 4-parameter model has only one parameter, epsilon, which is these radiative losses, which I would think is the crucial parameter that sets the nature of galaxies. So, so remember, so if you now look at the blue equation, so I say, if I know a halo with a given mass at a given redshift, then I know what is the rate at which it grows in mass. So I know what is m dot halo. Okay. So the right-hand side is purely set by cosmology. Give me a halo at a given redshift, and I can tell you what is the right-hand side. And that means I also know the star formation rate of this galaxy, provided I know this V star, okay, which I'm going to keep a constant. So given a halo, I can predict what is the star formation rate as a function of redshift. Okay, so that means I can write the star formation rate of a galaxy as a function of redshift in terms of what is the star formation rate at redshift of 0 in that halo times a function that only depends on redshift. Okay, so the functional dependence on redshift is here. It depends on the halo growth rate. It depends on the mass of the halo. It depends on the Hubble parameter, but it's the same for all galaxies. And here's the star formation rate now, which depends on the halo mass at redshift 0, okay, with some parameters that you can fill in. Kappa is 5/3, alpha is 1, the Hubble parameter, the value of V star here, and you get the star formation rate. So that gives you the star formation rate as a function of halo for all galaxies. So slightly nervous, I asked Mahavir to plot that out of the Eagle database to show you how that is in the simulations. And here is the result. So on the vertical axis, you have the star formation rate. The horizontal axis, you have the halo mass. Then the solid circles are the results of the Eagle simulation. The different colors are for different redshifts. So this is for redshift 0, this is redshift 1, redshift 3, redshift 6. And then the width here is a measure of what is the scatter around that relation in the simulation. Okay, so those are the simulation results. And then the solid lines with one free parameter are the models of these Eagles, of this IKEA model. Okay, the only thing that I varied is epsilon, which I took 0.1, independent of halo mass and independent of redshift. Okay, so a single parameter fit gives you the star formation rate as a function of halo mass as reproduced by the simulations. So I was slightly excited when I showed this plot, when I saw this plot first. So I think I'm going to skip this. So maybe because I want to understand why things, how these things evolve. So why is it then that the star formation rate increases with redshift? Okay. Well, one reason is that the halo accretion rate increases with redshift. Of course, we know that, right? Because that's what the simulations tell us. At higher redshift, the rate at which a halo increases in mass is much higher, for a given mass, is much higher than at low redshift. That's why the star formation rate of the galaxy is higher at high redshift. It's also because at a given halo mass, the virial velocity is higher at higher redshift. Okay, and those two contribute to explaining why the star formation rate is such a rapidly increasing function of redshift. Okay, so if you have the star formation rate as a function of redshift, you can just integrate the star formation rate and get the stellar mass as a function of redshift. And not surprisingly, if you reproduce one, then you reproduce the other one. So here is the model, the drawn lines compared to the simulation, the symbols for what is the star formation rate as a function of halo mass. Okay. So combined, I can now explain, or the model now explains the origin of the galaxy stellar mass function. Okay. Because I know for a given halo mass and a given redshift, what is the mass of the galaxy that lives in that. So provided I know the halo mass function, I can draw on that the galaxy stellar mass function. Okay, and in this model, the slope of the galaxy mass function is 3/5 of the slope of the halo mass function. Okay, so that explains what is the slope. And so the amplitude is set by the relation between stellar mass and halo mass at a given halo mass. Okay, so So back to the two plots that I wanted to explain, right? So I figured out what is the origin of the slope of the galaxy stellar mass function. Well, it's 3/5 of the slope of the halo mass function. It's about 0.54. So that's pretty close to what is observed. And also I get the amplitude, or the IKEA model gets the amplitude correct. It's set by the halo abundance. So what about the specific star formation rate? Okay, I don't know whether you have a plot on that. So specific star formation rate is a ratio between the star formation rate and the stellar mass. So if you substitute these equations that I showed you before, you get a relation like this. So you can evaluate that at redshift 0, and you find it's set by the Hubble parameter, by the recycling fraction, a property of the initial mass function, and by some dimensionless number that is an integral of accretion rate as a function of time. And so there's no more free parameters here, but it gives you almost exactly the observed value today. So one of the surprising things in that, so to summarize maybe, so the origin of self-regulation is now an energy argument. The galaxy loses energy to cosmological accretion. It gains energy because it's making stars, and it's a balance between those two that says the star formation rate. Okay, and the main uncertainty here is that a large fraction of the energy injected by supernovae is lost through radiation, and that is probably the most difficult parameter to compute in any model, be it a numerical simulation or an analytical model. What is maybe curious in all of this is that I haven't talked about gas at all. So this self-regulation model is very, very different from the model by Lilly, where self-regulation is due to the gas. I haven't even talked about gas up to now. Okay, I'm going to skip this. So let's be a little bit critical here. So I told you what is this relation between the amount of energy injected per stellar mass, the initial mass function, and this energy or this radiative efficiency here. Is this epsilon a constant? No, of course, it's not some constant. Can you calculate what it is? Well, I would say that's very, very hard. Presumably, it depends on density. For example, there's some very nice simulations that show that if you have clustered supernovae, those are very much more efficient at driving feedback than random supernovae. So it probably depends on density. It probably depends on metallicity, because once you heat gas, at the rate at which it cools depends on metallicity. Can I at least say something about the order of magnitude of epsilon? I would say it's probably 10% or so. 90% of the supernova energy is probably radiated, and simulations sort of agree with that. Can we measure this epsilon in simulations? Yes, but actually it's surprisingly difficult to do so. We haven't done this, and neither has anybody else. And so that's, so I would think epsilon is the main uncertainty now left in the modeling. So I think I'm going to, so if you're interested, not surprisingly, you get the relation between the stellar mass and the halo mass. You can calculate what that is for a population of halos at a given redshift. You can also calculate, so it's shown here. You can also show how that evolves for a given galaxy as it grows in mass. So let me talk a little bit about gas, because clearly gas is the fuel for star formation. So rather than using the star formation law to get the star formation rate, I'm going to use the known star formation rate to tell you how much gas a galaxy has to have. Okay, so what I'm going to do is assume that the star formation law is the Kennicutt-Schmidt law, relation between the gas surface density and the surface density of star formation. I'm going to assume that galaxies follow that without giving you any reason for why that's the case. Since I know what is the star formation rate of a galaxy, I can then tell you how much gas it should have to sustain this star formation rate. Okay, and so that is compared to the Eagle simulation again. So this is star formation rate. This is the predicted gas mass in the model. So those are the solid lines compared to the gas mass in the simulations. And not surprisingly, the model reproduces that because the galaxies in the simulation follow the Kennicutt-Schmidt law. Okay, so given that, there's something interesting you can do. So look at my dark matter halo here. It has some star formation rate and some gas mass. And I know, or at least I claim I know, what is the rate at which gas is added to that. Okay. So I know per unit time how much gas is added to that. I know what is the star formation rate, so I know what fraction of that gas goes into stars. I also know what is the gas mass, so I know what is the change in gas mass. But in general, the rate at which gas is added to a halo is much bigger than the sum of the star formation rates and the change in gas mass. Okay. So then simply counting baryons, where do these go? Okay. And so the prediction is that for this model to be consistent, a large fraction of the gas that accretes onto a halo must leave it as well. So it has to be, for this model to be consistent, that galaxies drive a strong outflow. And of course, we know that from simulations that that's true. So here are some outflow properties. Okay, so these are, I want to go very quickly about this. So this is the ratio of the mass in the outflow or of the star formation rate, called the mass loading, beta. So let's just concentrate on that. So there's two panels. I plot this as a function of halo mass on the left. So this outflow as a function of halo mass, and outflow rate as a function of virial velocity is maybe the more interesting one, because then you see that all halos track the same line here, independent of redshift. Okay, and this line goes in the sense that at low virial velocities, the mass loading is very, very large. Okay, and as the virial velocity gets higher, the outflow rate decreases. And in fact, there's some characteristic virial velocity above which the outflow stalls. What is going on here is that the potential of the halo is now so deep that the supernova cannot expel gas from the halo anymore. Okay, and so that's curious, right? What does this mean for self-regulation? Well, it means the failure of self-regulation. It means that for halos which are so massive that they fall to the right here, that they cannot self-regulate due to supernova feedback. So everything breaks down here, okay? So self-regulating galaxies live here, and then as they get too massive, self-regulation fails. So I'm going to skip this. So the failure of stellar feedback here. And then of course, then the question is, so what happens to a halo then? Well, who knows, okay? So in a sense, this is the limitation of what the theorist can do. They say, well, my self-regulation of star formation fails. So then, says the even more ambitious theorist, I know what happens then. You feed the central black hole, because we know that these massive galaxies have central massive black holes in this. And so what I'm going to do is change my equation for self-regulation. Left-hand side here equals right-hand side. And I'm going to add a term which is due to AGN, okay? So now it's no longer star formation that regulates the forming galaxy, it's the black hole. So it's a very similar expression. So for star formation, you have m dot star times v star squared. Now you have m dot black hole times v AGN squared. So v AGN is again a measure of how much energy the AGN injects per solar mass of increase in black hole mass. And if you integrate this equation, you get a relation between black hole mass and halo spherical velocity, which is the blue line, which is very close to the observed line. So not surprisingly, it's now the black hole that takes over, and that gives you the observed relation between black hole mass and virial velocity. So I have a quick look at my timer. I think I have a couple of minutes left.
That's okay. You can,
it's okay?
You have 5 or 10 minutes.
5 or 10 minutes. So I have some, so this is, I think, so as far as the IKEA model is concerned, so this is what we wrote up. And so maybe to summarize, so the motivation for this model is not to come up with the best fitting model or to have some model with 1,000 parameters that goes to the exact data points. No, the point of the model is to reveal the physical processes of self-regulation. Why is it that all these different simulations, although they do something completely different, yet they come up with the same answer? Okay, and what is the main physical process that regulates the forming galaxy. Well, it's this energy regulating argument that is on the screen here that relates the star formation rate to the cosmological accretion rate, and that, I think, explains most of the behaviors of the galaxies that we see in simulations and also in the observed universe. Details are important, right? So this is not meant to replace the simulations or semantic models. Rather, it's to give you some hint of what is the underlying physics. And so, so some more things that I thought about more recently come back to this growth in mass. So this is I showed this equation before. It's a fitting formula for how the halo mass function in simulations changes as a function of halo mass and redshift. And remember, so in the IKEA model, some of this mass comes in the form of baryons, and those are fuel the star formation in the model, right? And so the question is, can we see this accretion happening? Okay, so is there any way to check whether this gas is really accreting? So I thought of making a simple model for this in 3 stages here. The first thing I want to, so I know what is the accretion rate on the halo as a function of mass, right? What I don't know is what is the profile, what is the radial profile that this mass accretes, that this gas accretes onto the halo. So I went back to an old paper by Bertzinger in 1985, a beautiful paper, I think, that shows that in an Einstein de Sitter universe, there's a self-similar solution for the rate at which halos grow in mass, okay? And it's a self-similar solution, so it also gives you what is the density profile. And it's a power law. The slope of this power law depends on what the nature of the accreting mass is, whether it's collision null or collision less. And it also depends on what is the inner boundary condition. And the slope is somewhere between r to the minus 1.5 and the r to the minus 2.2. And so I've taken the steeper slope here, which is relevant for collisional gas in the case that there is no accretion shock, or the accretion shock doesn't propagate outwards, okay? So given that, so here is the predicted density profile predicted by Bertzinger. And so what I plot here as the drawn lines is what is the hydrogen profile around the halo as a function of the distance to the halo center for halos of different mass. So for a massive halo, intermediate mass, and a low mass halo. And it's a power law with slope r to the minus 2.2, okay? And so this accreting gas at low density is very highly ionized by the UV background. But as the density increases, this gas starts to self-shield, okay? And so I did some very simplistic plane parallel calculation of the optical depth through this spherical accreting cloud. And then I can find out where the gas is highly ionized and where it's neutral. So the dotted lines are now not the total hydrogen profile, but the neutral hydrogen profile, okay? And so in the outskirts, the gas is very highly ionized, and the neutral density is much less than the total density. But then as you move in, the gas self-shields, and now the neutral density is equal to the total density, okay? So those are the first 2 steps. So then you can calculate in your spherical profile what is the relation between the column density and the impact parameter. And so if you look at a low halo, a mass, halo of low mass, say, so at large impact parameters, the gas is highly ionized and the column density is low. Then as you decrease the impact parameter, B here, all of a sudden your sight line goes through neutral gas, and the column density increases a lot because the gas now becomes neutral, and then it becomes a power law reflecting the power law of the neutral density profile. So this model, where you have spherical halos with a power law density profile, and in the central bits self-shield, was already in this model by Zeng, this paper by Zeng and Meraldo Escudé. So they did a much better job in calculating the self-shielding. I just did very simple plane parallel processing, plane parallel calculation of what is the optical depth, okay? So for a halo of a given mass now, I know what is the density profile of neutral gas in the outskirts. I know where the gas becomes neutral. And so that means, provided I know the number density of halos, I can tell you what is the column density of absorbers at a given column density. And that is plotted here. So this is the column density through the halo. And this is the column density distribution function. So it's the number density of halos with a given column density. Okay. And so the colored lines here are the prediction of this very simplistic model for redshift 2 to redshift 5. Okay. They fall pretty much on top of each other, not exactly, but nearly. And they compare to, in yellow, the results from a numerical simulation, one of the these hydro simulations that I've been talking about that include full radius transfer. And it also compared to the symbols with error bars here, observations at redshift 2.5. Okay, and so you see that the simulations and the data are in very good agreement, but they're also in pretty good agreement with the model, within 50% or so. And so you see here that in the simulations, these high density absorbers called damped Lyman-alpha systems, they, as we knew already, they correspond to sightlines intersecting the neutral centers of the galaxies. Then you have this very rapid decrease here in the column density at an almost constant number density, where you go from neutral gas to highly ionized gas. And so then the model fits very nicely on the observations of Lyman-limit systems. So I would say that this accreting gas that you need in the IKEA model to fuel the star formation, that to get the right star formation in the galaxies, you see in the intergalactic medium as the Lyman-limit systems. Those are the outskirts of this accretion flow into the halos, and the damped Lyman-alpha systems, which are the centers of these halos. So that's it. So I don't think I need to summarize. So I think that maybe the main thing to take away from this talk is that Mavir and I have tried to come up with a physical process that explains the behavior of galaxies in terms of self-regulation, where a galaxy loses energy, becomes more and more bound as the halo, the potential well of the halo increases due to cosmological accretion. The galaxy resists that by making stars at a rate that aims to keep the energy of the galaxy a constant. And so the biggest uncertainty in the whole modeling is that a large fraction of the energy that supernovae inject in the interstellar medium gets lost through radiation. And so if you want to have a model that reproduces the simulations or the observations very well, you need to calculate a value of this efficiency, which reproduces, in order to be able to reproduce this. So in short, if simulations can reproduce the observations, it's because they have realistic radiative losses in them. So in the future, what else can you do with this? So I'm thinking of applying similar arguments to the evolution of quasars. I showed you that you get a realistic or relatively realistic black hole mass function out. Cosmological evolution of metals would also be neat. I haven't thought much further about how to do this. On a different track, I talked about the star formation law and this whole complex physics of interstellar medium gas getting denser, forming stars, getting less dense due to feedback. And I'm wondering whether you can apply similar reasoning to, in a sense, understand the origin of the Kennicutt-Schmidt law. All right, thank you very much. So now I'm very keen to hear your questions and comments. Thank you.
Great, thank you. That's an electronic applause for you.
Thank you.
I mean, the audience, Mahavir Sharma, your co-author is also here in the audience.
All right, excellent. Hello, Mahavir.
Mahavir is there. He can also take part in the discussion. There are lots and lots of hands up as soon as the talk finished, even though we told people they could ask questions, they were very, very well behaved. Before going on, several of the co-hosts also want to ask questions, but they can't raise their hand. So I'll start off by asking Surud More among the co-hosts to unmute and ask questions.
Okay.
I can't unmute you. And then I'll go to the other hands that are up. Surud.
Thanks, Shomak. So, Tom, that was a great talk. I just had a couple of questions regarding, I mean, all these models which are simple enough, they are great to understand the physics that goes inside in establishing some of these relations. But the question that I had was to the physics, right? So these accretion rate that you talk about, right? onto the halos, especially these low mass halos. If you look at them, and if you look at their physical density profiles, then oftentimes, even from redshift 1 to today, most of the evolution or the growth in halo mass that happens is just because of the background density falling down, and you tying the halo mass to an artificial boundary, right? Which is like 200 times the over density.
I very much agree with that. I very much agree with that, and I think so. So some of the evolution that you see here in the concentration, here and here, I think is exactly what you're describing. So I fully agree with that. So I would think that the model also, for that reason, works better at higher redshifts because you don't have this problem so much. So I fully agree with you. So I don't have in my mind a better way. It would be great to come up with a better definition of what is the halo.
Yeah, sure.
In order to.
So we have been working on these things related to the splashback radius. There are papers by myself, Andrei Krautsov, and Benedict Diemer, and others. So it would be great if we can actually try to, I mean, we have now been able to measure these splashback radii in simulations as well. And so it might be possible to define a halo properly and to understand the actual accretion that happens.
Right.
So that brings me to another question. So in your model, will it be correct that the star formation rate will somehow be larger?
Yes.
So we just recently, like a couple of weeks ago or so, we put out a paper, Peter Beruzzi, myself, and Christine O'Donnell, who is a student in Arizona, where we tried to figure out whether star-forming galaxies indeed have higher accretion rate onto their halos or not. And these were like Milky Way halo masses.
Right.
What we found is observationally, it seems that there is an evidence, but it's the opposite, which is if you have a higher accretion rate, then it's likely that you have a lower star formation rate. So the redder galaxies, which are, they have a higher accretion rate rather than the star forming galaxies. It's an intriguing, interesting result, but I don't know if you have seen that. And
I did see that. So two things I want to point out. So there's the accretion rate is here. So the star formation rate, accretion rate. Maybe I get a different one. This one. So star formation rate, accretion rate. There's this term as well. So that's a measure of the potential well of the galaxy. But maybe more important, maybe more relevant for what you're describing is that what this describes are the self-regulating galaxies. Are all galaxies self-regulating? No. In particular, the red galaxies that you're talking about are not. So I would say, this is a prejudice. What happens in the simulations? There's two reasons why you're red as a galaxy, why you're not star forming. One is because you're a satellite, and of course, for a satellite, they don't take part in the cosmological accretion, so that's irrelevant. And the other is, in the simulation, is galaxies where the regulation is due to the black hole. Okay, as soon as the black hole wakes up and starts to regulate the behavior of the baryons in the center of the halo, then I don't know what sets the star formation rate anymore. So I would say that the massive red galaxies are not described by this model here, because what regulates them is the black hole and not star formation.
That's right.
So
So we have tried to look at Milky Way halo masses and maybe slightly below, but it's hard observationally. And then we also tried to look at isolated galaxies to avoid this satellites and so on. But at least the observational probe, and this is all related to Bertshinger's models as well, where the splashback radius comes from. That I think is an observational tool that can be used in order to test some of these.
Right. So maybe the other thing to think about is that the scatter around these relations is quite large, right? So it's clear so I haven't tried to understand what is the origin of the scatter, although you may think maybe it's variations in the accretion rate. So in the sense, I haven't said anything about what the expected scatter is around this mean relation.
Yep, that's right. Yeah.
Great, thanks, Surit. Let's go on to other questions. Asim Paranjape.
Yeah, hi Tom. So
Hello.
actually, you already touched upon something that I wanted to ask about, which is satellites. So,
Right.
so do you think of the split between your regulating galaxies and satellites as a binary one, or have you also thought about satellites which might be regulating? And is there a role of environment then in the regulator?
So I haven't thought much about this. So my feeling would be that if clearly if the cosmological accretion is shut off because you're a satellite, and maybe you're losing gas because of stripping, it would be very difficult to predict from a self-regulation model what it is you're doing.
Mm-hmm.
So I haven't tried that. I haven't tried to see whether it's possible. So as long as you're thinking of high enough redshifts, then satellites become irrelevant. It doesn't really matter. It's more at low redshift that it become a bigger and bigger issue.
Because in the 2-slide summary that you would like to show Newton,
right?
I would add also the environment dependence of the bimodal distribution.
True. So yeah, I mean that's what I said, right? If you ask different people, they probably come up with different slides.
Anyway, thanks.
Thanks, Asim. Yes, I think environmental dependence would be my slide as well.
Okay.
Next, Kandu.
Great talk, Tom, and I
Thank you.
really enjoyed this thought of self-regulation. I was wondering two things. One is what sets the redshift zero normalization, because you had some unknown stuff. It looked there was a redshift dependence, but there was all kinds of things floating around.
I'll try to come to that. Let's see where I can find this. So
yes.
So look at this. Look at this function psi of z here, right? Yeah. So that's all cosmology, right? There's no galaxies here.
Yes.
So this is the halo mass as a function of redshift, and this is the logarithmic growth rate.
Yes.
Okay. So psi of z is purely set at properties of how halos evolve in your particular cosmological model. And so if you now say, well, I want to get the stellar mass of a galaxy, what you need to do is integrate this psi of z function.
Right.
Okay. And that is what this parameter m star is. Let me see where I can find this. This thing m star here is basically the integral of this psi of z function.
Okay. So it's not calculated a priori, but it's set from observation.
Well, it's calculated based on fitting the evolution of dark matter halos.
Okay, conserving stuff, yes.
And so if you then say, so what is then the specific star formation rate? So it depends on that. So capital R, I went very quickly over that, but is the recycling fraction. So the integral of the star formation rate is not the stellar mass because stars lose mass.
Yes, that's clear, yes.
So that was the R here, and H naught is the present-day Hubble parameter. So that's all in it. If you want to say what is the specific star formation rate today, it's those three that sets the value today. So I was slightly worried when I started calculating that to see whether this would come out right, because there didn't seem to be any reason for this to come out right. But you know, so minus 10.1 is here, so it's almost almost spot on.
And there was a slope to this mass loading versus the velocity.
Yes.
Is that consistent with either energy or momentum conservation in the outflow?
So I went very quickly here. I only talked about the mass loading, and that is basically a counting argument. I know how much gas goes into a halo. I know what fraction of that gas goes into stars, what fraction goes into the gas reservoir, and all the rest needs to leave the halo.
Yes.
And so this in itself doesn't assume anything about energy-driven or momentum-driven.
Right.
If
so
you
I'm
say
just wondering whether it's consistent with V squared dependence or V dependence.
So
that slope against the velocity.
Yes, I guess I should know that, but I don't. No, I do. Here, no, I don't. Sorry, I don't. No, but I can calculate. Maybe it says it's in the paper. I don't know. So if you say what is the speed that this gas leaves the halo, then you need to make some assumption whether it's momentum driven or energy driven. And so the
Right.
bottom plots assume it's energy driven, but that's an extra assumption.
Yeah, I mean, the beta should depend upon whether it's energy or momentum driven, but we can discuss it later. Yeah, thank you.
Okay.
Thank you.
Great, Kandu. Thank you. Next question, Prakash Gaikwad. Prakash, can you unmute? I've trying to unmute you. Yes, go ahead.
Hi, Tom. Thanks for very
Hi.
nice. Yeah.
Thank you.
Please, you're comparing your models with simulation. Right?
Yeah.
The simulations use some kind of subgrid physics.
Yeah.
So do you think that by changing the subgrid physics in different simulations will converge the result? I mean, the correlations would be same, or will it be different?
So it's a good question. So let me go to the beginning, right? So I showed you all these different models and how well they reproduce the data. So here, right? So all the different colors are different models or different simulations. So as you say, these do quite different things. So the subgrid models that you describe from one model to another are very, very different.
Yes.
So do the results depend on the
Yes.
choices? Of course, right? And it's one of the things that makes simulation so difficult. You have some subgrid model that has some parameters. You don't know what these parameters are. So then you pick one, and then maybe you make too many stars or too few stars, and then you change it, and that makes it very hard to get these simulations to give you the observed answer. But so clearly, many of the modelers have been able to pick parameters that within their model give you, reproduce the observations. But I would argue from that, this is great, right? This is very impressive that you can do that. However, since you can get the same answer with different subgrid models. So the parameter that you've calibrated doesn't really mean much, because you can do something completely different and still get the same answer. So that's what I saw. One of the motivations of IKEA is to understand what is it then that you need to get right. Clearly, it's not a particular model parameter. So what I would say is what you need to get right is that the feedback from your stars is efficient. Okay, and there's many ways of doing that.
Yes.
But as long as you manage to get them efficient, self-regulation will get you the right star formation rate. But only provided that your feedback is efficient. But how you do that doesn't matter. So in particular, there's some of the subgrid parameters that are almost irrelevant. For example, the star formation law. So you would think the relation, so the star formation law means what is the relation between the gas mass and the star formation rate. Okay, so you would think clearly that sets the star formation rate. That's such an obvious statement that you don't even think that's maybe not true. But that is not true, because if you change, so that you can show that in simulations, you change the star formation law and the star formation rate of the galaxy doesn't change. And you would think at first that's impossible. But the reason for that is that if you change the star formation law, you change the gas fraction. Okay, but not the star formation rate. And so that of course is one of the motivations to look for self-regulation, right? So there's large swathes of these subgrid parameters that do not affect the star formation properties of the galaxy. They may affect the gas mass and hence the metallicity of the stars, but not the star formation rate.
But they will also affect the CGM properties, right?
They will. So I agree with that. So if you change the star formation law, you change the CGM properties. Yes. Yeah.
I mean, in that sense, the observations will not match for some simulations.
Exactly. Yes. And of course, but comparing the CGM, the observed CGM to simulations is at the edge of what we can do. I think, right? Many people have pointed out that that's, for example, very sensitive to numerical resolution. Maybe not surprisingly, right? So at the moment, the simulations do quite well,
Mhm.
and I'm not sure whether that's just a fluke, because they might not even resolve the structures in which the carbon 4 or the silicon 4 or the carbon 2 is detected, right? So
Thanks.
Hello.
hello, was I clear?
Yes, Shamak. Oh, Shamak is.
Sorry, I'm muted.
Ah,
Sorry,
okay.
sorry, go ahead, Srianand, go ahead, and the next question. I just said that Tom has agreed to be here for discussions with the smaller group too afterwards. But there are many questions coming up anyway. Srianand, go ahead.
Hi, Tom. It was an interesting talk.
Thank you.
I have a question related to your gas distribution in this later part of your talk.
I put it in especially for you. So,
Yes, I was wondering because in the past I remember such attempts usually doesn't capture the redshift evolution of TLAs, right?
yeah,
So you are able to get it right, or what? Because
yeah, I am baffled by that as well. So I can show in the modeling why this independence, why it's so little dependent on redshift. Okay, it's very, very, very weakly dependent, as you can see, right? It's very, very weakly dependent on redshift. And I'm struggling to understand why the previous models didn't get that. So I've no good answer for that. So I can explain why my model is so little dependent on redshift. Basically, it's a fight between so the viral radius of galaxies, of course, grows, but then as the density of the universe decreases, the region in which they self-shield decreases. So the cross-section decreases, but the number density increases. And both of them are actually weak functions of redshift. And in addition, they work in the opposite direction. That's why there's almost no redshift evolution.
so your background you are using this background is constant, right? Because in this redshift range, our UV background will start
UV
decreasing
background.
between redshift 3 and 5. It sharply decreases.
So I use the Hartem-Edow for that.
Okay.
But I think that's yeah. I can run a model where I just keep it. Maybe I did that actually.
So what will be interesting to look at is now in your model you have a characteristic impact parameter, or whatever you call, what is the size cross section with respect to the galaxy.
Yeah.
And now there are more measurements which are coming in. We always find they are at a larger radius. So it will be interesting to see
what is the radius,
whether this simple physics captures, because this is a good idea, because at low redshift this is what people try to do to the truncation, right? Because what you are trying to do is equivalent of truncation radius of H1 disks.
Exactly.
You can observe.
Yeah.
So it will be interesting question to ask in this way. So I was struck by this constancy. That's why I was.
Yeah. Thanks. Yeah.
Okay. Thanks, Tom.
Thank you. Thanks, Pratik. Go ahead, Pratik Sharma.
Yes. Thanks. Very nice talk, Tom. I enjoyed it.
Thank you.
So I come from the more massive halo side. So I worked on galaxy clusters and so on.
Right.
But the whole, the big picture that you are sort of building here is the whole essence of feedback, right? Whether it's in AGN halos or in, or in star forming halos. So one, I had a doubt about one thing. So in galaxy clusters, for example, you made this analogy with stellar, main sequence stars.
Right.
And you said that, you want something which is equivalent of luminosity of a star, that is loss of radiation, and something which is equivalent of nuclear fusion, which stops the collapse of a star.
Mm-hmm.
So the thing that stops the collapse of the star, you made, I agree with the correspondence that you made. It's some sort of feedback, whether it's supernova feedback or AGN feedback. But in terms of the energy losses part, in clusters, for example, all you need is really to be able to balance cooling losses in the core. right? So then this is the cooling flow problem, right? So it's not obvious to me that you can just use the large scale estimate for the rate at which the halo is growing. Basically, E dot is what you put in as luminosity. So it sort of seemed very crude to me. So that's one thing, and it's actually related to Sir Hood's point, which he made. Really, he was the one who asked the first question, that observations don't show a very tight correspondence between m dot and the star formation rate at the center.
Right. So
yeah.
So first of all, so I think I very much agree with you that applying this to clusters of galaxies.
No, I'm not saying about clusters. What I'm saying is it's not obvious that the what you want to balance by supernova feedback is this E dot that you're sort of cooking up.
Yeah, so remember, one of the striking features of both observations and the simulations is the rapid increase of the star formation rate with redshift, right? So if you look at so shown here, right? So you look at the halo of a given mass, say 10 to the 11, you look at it at redshift 0 in blue versus at redshift 6 in purple, you have an enormous increase in star formation rate.
But so is there an enormous increase in the critical density of the universe, right? The density of the universe.
In terms of cooling. So that is of course true. I think one way to look at this is that, and that's why also I don't think you should apply this model to clusters. It assumes that the gas is available, that the accreting gas is not halted on its way because it's hot and doesn't cool. So I think in all cases, be it at low redshift or at high redshift, it assumes that the cosmological accreted gas is actually available for star formation. Clearly, so I made a big point that I can calculate the star formation rate without referring to the gas. But of course, it does assume that the gas is available for star formation. Right. So if it can't cool because it's in a cluster of galaxies, or because it's or it remains in the halo of the galaxy, then clearly what I've assumed cannot work.
But even for low mass halos, low mass galaxies, if you calculate star formation efficiency, like a global star formation efficiency, stellar mass divided by the halo mass, that's actually pretty low. Right. So in terms of being able to convert baryons to stars, it's sort of globally very, very low. Even so that was
So the reason for that is that this V star is large, right?
Yes.
And so remember, the V star needs to be V star large, meaning that the feedback is efficient.
Yes.
And so that is what we find in simulations. Feedback needs to be very, very efficient to reproduce the observations. And that's another way of saying that only a tiny fraction of the accreted gas goes into stars.
Right.
Hence why you have the strong outflows, right? It's just a baryon counting thing. So
okay. Yeah. Thanks. I had a lot of other questions, but maybe others can go ahead before me.
Thanks, Pratik. We can come back to Ron. It's Desh is next, Avinash Deshpande. Desh, can you unmute?
Yeah, I have a simple question. Great talk. I missed parts of it, so that's why the origin of this question. What is the typical value of epsilon that fits the observations best, in the comparisons? Because that was one of the key three parameters you had.
It is. It absolutely is. So in the plot that we're looking at, it's 10%.
Okay.
So meaning that 90% of the energy injected is just radiated away and doesn't do anything.
All right. Thanks.
Yeah.
I was groped for that.
Shantanu, do you want to ask a question? Shantanu.
Yeah, so this is a very basic question. Okay, so I mean, in the beginning, in the initial slides, you talked about Tully-Fisher relations. So I guess, do your simulations reproduce the baryonic Tully-Fisher relation with a very tight scatter as found by McGough and collaborators?
So the simulations do, yes. Yeah. So we have several Eagle papers on the Tully-Fisher relation. I'm just trying to find the slide here. So in some earlier version of the paper, I tried to include a Tully-Fisher relation. So in the IKEA model, the Tully-Fisher relation would be due to the circular velocity of the halo, right? So you get, many people have done that before, for example, Van den Bosch, saying that if there's a relation between stellar mass and halo mass, the halo have a constant circular speed. That gives you a relation between stellar mass and circular speed, and that's the Tully-Fisher relation. But in the end, I took it out because people had done this before. But the simulations themselves reproduce the Tully-Fisher relation quite well, yes. Yeah.
Great. Kanak had a question. Kanak Saha.
Hello.
Hi,
hello.
Go ahead, Kanak.
Hi, very nice talk. I enjoyed listening.
Thank you.
Kanak, speak loudly, we can't barely hear you.
Yeah, I have a very simple and naive question.
Yeah.
It's like you talked about the self-regulation, and I wanted to understand, so what would be the key observational prediction for a self-regulated galaxy? How do I recognize if I look at a bunch of galaxies in the...
That's a good question. I don't have a good answer to that. I think in the simulations, so for example, let me go to the one of the plots, right? So the specific star formation rate as a function of stellar mass.
Mm-hmm.
So I guess self-regulation would mean that, but I don't see how you can observe this, that that galaxies are attracted to this line here, right?
The slope zero?
Not just the slope, but that. So if I claim that it's because of self-regulation,
Okay.
that there's a relation between the star formation rate and the halo accretion rate, right? That's the basis. Then that means, so maybe this is not the right plot because this gives you stellar mass, but it should be an attractor then, right? So so let me maybe go back to this thing here. So let me find the slide here. Right. Okay. So the essence of self-regulation is that if a galaxy has too low a star formation rate, given its halo accretion rate, that then it increases its star formation rate. That's the essence of self-regulation.
Yes.
So, but how you would do this observationally, I'm not 100% sure. In simulations, I guess you could measure this and measure that and see what happens to galaxies that are below. Yeah.
Yes, because you can't do the halo accretion rate in the observation.
In the real universe, right? That would be difficult to do. Yeah. So, but maybe there's a better way of doing this. But I don't know at the moment. I don't have a good answer to your question. In the simulations, yes. Well, actually, maybe you could then relate the scatter around the main sequence to scatter in the accretion rate. That
okay.
You know, that might be one way of showing consistency between the model and the observations.
Okay. And the scatter, is there also sort of some prediction, because the scatters are also different in different redshift?
I'm sure people have measured that, but I wouldn't immediately know who. So the Korea paper that I'm using uses a fit to the mean buildup of the halo as a function of redshift. But I'm not sure that they looked at scatter. They might, or somebody else might have looked at that, but I haven't looked at this at all.
Okay. Thank you.
Great, thanks. I mean, we've had a very good discussion, and I'm glad to see that most of the people who started off are still there.
Okay.
The huge panel in here. I was wondering if anybody else had any issue to raise. Pratik, did you have any more questions to do?
Yeah, so Tom, I will try to write an email to you to set up a time when we can discuss.
Yeah, yeah,
okay.
Great.
Thanks.
Pratik, go ahead. Unmuting you.
Yeah, thanks. Yeah, so it was very, very good talk. I enjoyed it. So a lot of questions actually, but I'll just ask one, which is, why doesn't black hole act in low mass galaxies? What is it that tells the black hole that no, now is the time that halo is big enough that you have to act?
I think that's a very good question. It's not 100% clear to me what the answer is. In fact, some people would argue that also low mass galaxies are affected by their accreting black hole. I think there's a lot of discussion about that.
But you are not arguing that. You are clearly saying that it's
the black holes in this model were like an afterthought. So I haven't thought too much about this. And so what I find interesting, so I'm not answering your questions, I realize that.
No, that's fine. These are tough questions.
But so what I find interesting in this aspect is what is cause and what is effect. So in the simulations, so in the Eagle simulations have black hole feedback. And so we inject, or we endow, I should say, every halo with a black hole particle as soon as the halo is above a mass of 10 to the 10 solar masses. Okay, and then we put a black hole seed in it, and that black hole seed can do whatever it wants. So it can accrete matter and grow in mass. It can merge as halos merge. And what we find in the simulations is that on average, in little galaxies, these black hole seeds don't do anything. Okay, they may accrete a bit. Okay, but in general, the galaxy is star forming, and if you were to take out the AGN feedback, the galaxy forms stars at almost exactly the same rate. So although we don't do anything to prevent the black holes growing in little galaxies, they don't. Okay, of course, the model may be wrong, right? But that's what we don't do anything and nothing grows. And there is a reasonably well-defined real temperature of the halo above which this changes. Okay, this is about 10 to the 7 Kelvin. As soon as the real temperature of the halo gets above that, then two things happen. First of all, most of these more massive halos have a hot halo, whereas at lower mass, a very small fraction of the gas is hot. Okay? So you develop a hot halo and the AGN starts to grow, or the black hole starts to grow, and AGN feedback starts to set in. That's number two. And number three.
But even in Milky Way-like halos, people argue that most of the baryons are not in stars or in the ISM, right?
So the Milky Way is a good example because that's at very much at this transition. Okay, so at very similar masses, you have galaxies like the Milky Way, which have a puny black hole, or you have a galaxy like Andromeda, which is very, very similar in mass, probably in halo mass, but its black hole is much more massive. And so the Milky Way seems very, very close to the edge where you change from regulation by stars to regulation by black holes. But exactly what sets that and what is now cause and what is effect is not so clear. So Richard Bauer has a nice paper about this. So he claims that is set by the entropy of the feedback. Okay, so think of the supernova heating gas increasing its entropy, and compare the entropy of that gas with the entropy of the gas in the halo. If the entropy of the feedback gas is lower, then feedback is efficient because feedback gas can float up, say, right? Buoyantly. And so that is set by the properties of the feedback. And so in Bauer's model, that's why as the virial temperature of the halo gets too high, now the halo gas has higher entropy than the feedback gas, and so stellar feedback fails.
Right.
And so basically the galaxy cannot get rid of its gas. And so exactly why this feeds the black hole is still not obvious to me. Maybe it's that the star formation rate is too low to consume all these gas, and then it just falls to the center and feeds the black hole. And once the black hole switches on,
sort of like if everything fails, the black hole will take care of it.
The gas needs to go somewhere, and if the galaxy just fills up with gas, then eventually the black hole will take some of that, and then once it gets going, there's no turning back.
Good.
Thanks very much, Pratik. I think we should round off today. I mean, a lot of people are now leaving. So unless there are any more questions, I'd like us to applaud and thank you very much, Tom, for this amazing.
All right.
And the discussion that followed. A lot of people are still wanting to, I think, ask you questions. They might email you later on.
Okay, really
hope
fine.
to see you back again with us.
All right. Thank you very much. Thank you for all the questions.
Thanks, Tom.
Thank you.
Thank you very much.
Bye. Bye-bye.